Hello, my name is Herman Retana from Incai Business School in Costa Rica, and this video is about application architectures. This is not a video for engineers, but rather for business executives, and I'm trying to show you in this video the very basic things that every business executive should know about application architectures. And in line with the photograph in this cover page, what I'm trying to express over this video is how are we stacking up the different software elements in software applications such that in the end we have a software application that simply works regardless if we understand how exactly it was built. So the overarching question underlying this video is how are the different elements behind any software application we see out there in the wild organized? How is it that software applications are built up? Throughout this video, we will start by talking about the different types of application architectures. We'll talk about how can we classify these architecture, and then given each model, we'll discuss what are the pros and cons of each of the models. One of the most popular models is the client-server architecture, which strongly leverages the concept of middleware. So we will talk about what middleware is, talk about APIs, and more broadly or more currently, we'll talk about integration platforms. We'll then put all these elements together in what we call multi-level or multi-tier architectures. Finally, we'll devote quite a bit of time on how is it that these different software elements are installed within different pieces of hardware. We want to clarify what is a physical hardware and what is a software application that serves a certain function or service. And towards the end of the video, we'll go into more modern types of architectures, such as those based on containers or microservices. But let's get started with the different types of application architectures. What are we talking about when we refer to application architectures? We are referring to the way in which the four basic functions of applications are distributed between clients and servers. And what are these functions? The first ones are going to be data storage and data access. Basically, at some point in the application, we need to be able to store the data that the client, that the user is working with, and we need to store it somewhere in an orderly fashion. So this is the functions of data storage and data access. Then we need to manipulate this data, and this is going to be done by what we call the application logic. This is where we manipulate the data that is stored somewhere. Examples of softwares that manipulate data could be the traditional ERPs or supply chain management systems, CRMs, also text processors such as Microsoft Word or spreadsheet software. Any software that we use to manipulate data, we would consider part of the application logic. And finally, we have the presentation logic, which is also known as the graphical user interface. It is what the end user uses to interact with the software. It's the part where we have a screen and a keyboard and a mouse that we use to interact with the application itself. So given these functions, these three broad sets of functions, we can actually define three general models for application architectures, each based on who performs or takes care of each of these three elements. And let's start with one of the oldest ones in the books, which are server-based architectures. And when we hear about mainframes, we're referring to these old school kind of architectures where everything was centralized in a single big, very, very powerful mainframe. Now, quite ironically, this is also what we're looking at when we look at cloud-based services with very thin clients. I'll come back to this in just a second. When we say that these are server-based, we're referring to the fact that most of the workload is taken care of by the server. In this sense, not only is all the data stored at the servers, but also all the data is manipulated on the server side. What we have at the client side is a very thin client. Back in the day of mainframes, we had dumb terminals. These terminals only had a screen that received video signals from the mainframe and a keyboard by which the user would send signals back into the mainframe. But what the client had in front of him was nothing more than a dumb screen and a keyboard that would transmit and receive data from the mainframe, from the server. The client's workstation was not even a workstation because we didn't do any processing of the data locally on the client side. Something similar happens nowadays with very thin clients such as smartphones or tablets that we use to access very powerful applications that almost entirely run on cloud-based servers. So we could also refer to these cloud-based applications as server-based application architectures. There are also some applications where we actually do install and do leverage some processing power on the client end. And these are the very popular client-server types of applications. Once again, we have both the server and the client are both processing data. So even though most of the data is stored on the server side and we still have a client taking care of the presentation logic, we will have an application installed both on the server and on the client. Examples of these might be ERP systems whereby we install an ERP application server on a physical server, but we must also install the ERP's client software in our client laptop. In this sense, the processing of the transaction is taking place both on the server side and on our clients and on our laptops or PCs. Finally, we have client-based applications in the sense that now everything runs in our own laptop. Simple examples of these are standalone applications such as Office suites where I open the application to manipulate the document that is stored in my computer and I save it. Everything is going on my computer. We could also have applications that run entirely on clients, but these clients communicate with each other in what we call peer-to-peer networks. Old school software such as BitTorrents, where all the users go in and share in a common network all the data to transfer data, not necessarily legally, but that's another story. But the cool thing about BitTorrents is that there are no servers organizing the data. It's a lot of clients talking to a lot of clients. In a more modern scene, we can find that technology such as blockchain is peer-to-peer networking, where there's no centralized server holding all the data. Rather, all the clients have different copies and versions of the data, and the clients communicate with each other. Now, let's take each of these three models and discuss the pros and cons of each, as we also recap some examples. Going back to the server-based, we mentioned that these were applications based on mainframes or also web applications. The software as a service offerings we find nowadays are also server-based applications. Think of online office suites such as Office 365 or Google Apps. What we have on the client side is nothing more than a browser, and all the processing power and the storage of the data is happening on the server end. What do we earn by running server-based applications? On one hand, we have centralized management, in the sense that if we need to make any change to the application, we only need to change it on the server side. Once we change the application running on the server, it is automatically updated or changed or altered for all the clients accessing this particular server. Moreover, we can have very heterogeneous clients, and basically any client with the capability of connecting to the server or accessing the server will in turn also have access to the application that is running in this server. On the flip side, especially if we're talking about mainframes, we find that the server may become a bottleneck. Everyone is relying on a single piece of machinery, a single piece of hardware. And if this server starts failing, then the server quickly becomes a bottleneck. Moreover, if we want to be able to run all the bulk of the applications on a single piece of hardware, it is likely that this large mainframe, this large hardware is going to be very expensive. And in terms of financial capital, we require a very strong investment to run such a big hardware. Finally, again, given that we have a big, bulky, chunky hardware, it's going to be quite hard to match the supply of computational resources with the corresponding demand. If we have underused capacity, it's going to be very hard for us to get rid of a portion of a server because we can't really split our hardware in half. And once again, this applies mainly to mainframe-based applications. In the cloud, the story is quite different, but that's not part of the scope of this particular video. Moving on to client-based applications. And once again, examples of these are going to be applications that we install and that we run from our laptops. And applications such as Office suites, statistical packages, basically anything that we install in our laptops and run from there will be considered a client-based applications. We also have the P2B environments such as blockchain. Contrasting this with the prior server-based context, clearly we now have lower capital investments. Buying individual workstations, individual laptops for users is much less expensive than buying a bulky mainframe. By the same token, since we have smaller units of computing capacity that we are acquiring over time, it is going to become easier to match the supply of computational resources with the demand. Namely, we can buy a laptop that matches specifically the computational needs of every individual user. Now again, contrasting this with mainframes, just as how in mainframes we had centralized management and that was a pro, Now we have to manage independently each of the individual workstations of the users in a very complex decentralized management setting. Suddenly updating the software implies making deployments and updates on all the different workstations on the hands of all my different users. More importantly, if the data is spread out across multiple clients, syncing the data across the clients is going to be hard. Think of the classic example of everyone working on the same homework on their files on their laptops, and then no one knowing who has the latest version of that particular homework or task. In between these two models, we find the client-server examples. And the classic examples of these are going to be information systems such as ERPs. We could also have BI software where we have a server storing the data and manipulating the data somewhere, and then we have all the visualization engine running on the client side. Old school mail systems such as Microsoft Outlook, for instance, where we installed the Outlook client on our laptops to connect to a mail server, would also be a classic client-server example where we have software running and processing data both locally in our clients as well as remotely on the servers. The key benefits of client-server architectures are going to be the distributed processing, in the sense that now there are no bottlenecks because everyone is doing part of the workload. And given this, it is also relatively easy to scale the computing capacity where it is needed. If we feel that the clients are failing down and we need more capacity, we invest in the clients. If we have multiple servers running different things, we can start upgrading different servers independently. We don't have to invest in upgrading the single bulky mainframe. We can start upgrading the individual and independent servers. Something that's going to become clear when we talk about multi-tier applications is that client-server architectures allow for multiple hardware and software of various vendors and providers to work together. So it enables us to have very heterogeneous ecosystems or very heterogeneous application architectures and have everything working together. Now, with this heterogeneity, with this variety and all the different moving pieces that we have an increased complexity. And this is the key disadvantage of client-server architectures. We have increased complexity that in turn drives complexity in troubleshooting applications because we don't know exactly what part of all our entire architecture is failing. This also goes in hand with our need of configuring middleware. But let me actually stop pros and cons and devote some time into discussing how is it that client-server architectures work based on middleware. So what is middleware? In layman's terms, we can think of middleware as the glue that bonds the different software elements together. More formally, we can talk about a software element that connects two other independent software elements. Let me give you an example for this. Let's assume we have an application server that is running standalone and that multiple clients, multiple laptops in my example, need to connect to this particular server. They need to interact and extract data from this particular server. The mechanism by which they're going to be doing this is generically called middleware. So once again, middleware is the generic term we're going to use to refer to the mechanism that two different software applications use to communicate with each other. In this case, we have the client application on the client end and the server application on the physical server, and they're communicating with each other through middleware. This could be an application server running an ERP, and it also needs to connect to a database server. So the application server running the ERP needs some middleware to connect to the database server. Also, it is likely that this application server is joined in the firm by an authentication server, some server that will enable me to demonstrate or prove that every user is who that user claims to be, and need a way that the application server communicates with the authentication server to know who is who and validate the authenticity of the communications. Back to the examples of peer-to-peer networks where we have clients communicating with clients, well, we also need a middleware for the different clients to communicate with each other. So with this example, it becomes clear that middleware is basically that software that enables any two elements in my application architecture to exchange messages with each other, to communicate with each other. And one of the key benefits of using middleware is that it enables us to isolate changes in each application element from changes in the others. Think of an example where a user is connected to a given application server and this user is changing its laptop's operating system from Windows to Mac OS or vice versa. Well, we don't need to change the server's programming to be able to talk to the different operating systems on the client side. Rather, the server only talks to a given middleware, and it is the different operating systems on the client side that know how to speak to this same middleware, so we can change the client's operating system without that impacting at all our configuration of the server. Okay, so this was a hypothetical example. Now let me give you some real examples of middleware that we use out there in the wild. Old school applications communicated with each other through the distributed computing environment, DCE, or the Common Object Request Broker architecture, also known as CORBA. These were the old messaging protocols that we used to exchange messages between one application and another. So we would develop an application that would speak CORBA, and the other application on the other end would listen to CORBA protocols. In more recent times, and especially with the advent of web-based applications, we have what we call RESTful APIs or REST APIs. REST stands for Representational State Transfer, and it is the widely used mechanism nowadays to exchange messages between applications that run over the internet. Back to more classic context, we have ODBC and JDBC. And this is basically the two most popular protocols that different applications would use to extract and interact with relational database engines. The image I'm showing you on the right shows the example of multiple applications that are ODBC compliant. They know how to talk to ODBC drivers. And different databases also know how to talk about ODBC. So if I wanted to use a given application to connect to different types of databases, to different relational database engines, I don't have to develop a different part of my software to speak to each individual and to each different database server. Rather, all what I need to do is to comply with some standard ODBC protocol, talk to some standard ODBC API, and once I know how to talk to this ODBC API, I can really start connecting with any other database that also understands the language of this ODBC API. Let me give you some examples of this, some of which I hope are familiar to you. One example that many of you might know is Tableau, the BI software. Many of you may have used Tableau to open static Excel or CSV files, but we can also use Tableau to connect to a Tableau server, MySQL server, Microsoft SQL server, Oracle server, basically a database server. I'm going to run this example with the MySQL server that I have installed in my own laptop, so the server is the local host. I give it a username and password, and at this point I'm going to be accessing a database server where I have stored multiple databases, one of which is called Notas MBA, which is my example. And in this database that has basically registrars for courses and students, I have two tables. One is called Estudiante, student in Spanish. I can tell Tableau to pull the data now and then rest at ease, or to automatically update the data it has loaded whenever the database changes in the back end. You can see that I have opened the table with the students, and now I can start manipulating, playing with the data. There's a column called Edad, which is age in Spanish, and I can use it to plot a histogram of the students' ages. And note that what I did was read data through a SQL query on a database. I did not open a static file. Another example I'm going to show you here is RapidMiner, the software used for data mining and business analytics exercises. I can also use it to connect directly to a database. What I do is that rather than creating a data repository based on a file in my computer, I tell RapidMiner I'm going to be connecting to a MySQL server on my local host. I'm going to briefly edit this connection to show you how it's built up, and you can see that RapidMiner has the capability of connecting by default to various types of database servers. I have chosen MySQL for my example. I also tell it what database username and password I'm going to use, and note that very importantly we're using JDBC, a different kind of driver, a different kind of middleware to access the data. Once I extract the data from the student database, Estudiante in Spanish once again, what I'm going to do is load this as a repository and simply load the data. And I'm not going to be running any models in this example because I just want to show you that I in fact pulled the same data that I pulled off from Tableau. And I'm going to show you some descriptive statistics on the students' ages. Just show you the observe a histogram and note that it is the exact same dataset that I had opened before. Many other software enable us to connect us to databases. A strong statistical package that I use for my research is called Stata, and I just want to show you that Stata in its import functions allows me to pull data from static files, but it also allows me to connect to an ODBC data source, namely any database server engine that I have out there that understands ODBC. And finally, I want to show you how Excel can do this. Excel, if you open it and go to the Data tab, there are various options that enable you to import data into Excel from a live database. Since it's a Microsoft product, it of course comes with SQL Server as the first option, and here I could simply give it the name of the database and pull data out of there. Overall, what we have are multiple options to move data in a very fluent manner from one software to another. In particular, once we are running any client-side application, we can use ODBC or JDBC, or more broadly, we can use middleware to go and pull data out of any standard database. So this is with the examples. Let's move on into more complex multi-tier architectures. Because so far we've only had a client connect to a server, but we could have a client interacting with two or more servers in what we call multi-tier architectures. Now, before we get into the complex architectures, let's recap the two-tier architectures that we've already seen and that are quite popular in simple local area networks. One example could be, and I know I already told you about this, that we have a client application for our mail, such as Mac Mail or such as Microsoft Outlook, and we're connecting to a mail server where our mail messages are stored. Another example, leveraging on the ones I just showed you, is that I have a business application desktop application such as Tableau, and I'm using this application to pull data from a database server that could be running MySQL, Microsoft SQL Server, Oracle, generally any other relational database engine system. Now let's move to more complex settings, a three-tier architecture, for example, where you have one client and two servers. And let's go back to our mail example. Many of us nowadays access our email through a web browser. So my client does not have any software installed. What I have is a web browser. This web browser is loading a web page that is serviced or offered by a web server. And this web server in turn is pulling data that is coming off a mail server. So our web browser is not connecting directly to the mail server. Rather, we're connecting to a web server, which in turn is connected to the mail server. Another example of a three-tier architecture is how most ERPs run. When we have an ERP system installed in a laptop, we have a client application installed in our laptop that is connecting directly to the application server where the business logic of the ERP is processed. And this ERP application server is in turn connecting to a database server where all the data is stored. Note that here we also have two servers and a single client application. Now this could go on, and we could have more than three tiers. We could have what we call an N-tier application with more than three elements. Let's go back to an ERP system, but this time we're accessing that ERP system through a web browser. So on the client side, we have the client browser that we use to connect to any given web page. We're connecting to a web server that is servicing that web page. That web server is loading data from an application server, which in turn is manipulating and processing the data of the database server. So the application server could be the ERP that is running connected to the database, and we're accessing the ERP by means of a web page that is offered through a web server. And applications can get much more complex than this, but I think that with this example we already have the concept clear enough at least. Similar to the pros and cons that we had in basic client-server architectures, the key benefits of having these multi-tier architectures are that we have distributed workloads, that they are easy to scale and very flexible because we can change any given part that needs upgrading or better performance. We can focus and improve that particular element. Of course, the more moving parts that we have, the greater the complexity of this architecture, and thus it is much harder to troubleshoot and find the root cause of different elements. Now I want to talk to you about a specific example of middleware that we call APIs. And I already mentioned RESTful APIs earlier in this video, but I want to go deeper into the API concept. API stands for Application Program Interface, and it is nothing more than a certain module or element of a given software application that is exposed or made available to other software applications such that these other applications can talk to the focal application. So it's basically something I need to develop in my own app such that other apps can talk to what I have developed. And let me use the example of smartphones to exemplify what an API is. We all know that there are different vendors manufacturing the hardware of smartphones, and that smartphones can run multiple types of operating systems, most commonly Android or iOS. And then these hardwares, the physical devices, offer elements that different software applications want to use, like for example the microphone, or access the photos stored on this phone, or access the camera so that we can actually take photos, or access the GPS of the particular phone. And there might be an application such as Snapchat, and I know you've seen this before. When we install the app, it says this app wants to access your photos and the camera. And this is the operating system asking us if we grant this specific application access to the photos and the camera of this particular device. Applications such as Instagram could access the same devices. Other applications such as Waze might ask us to access the camera and the GPS. And applications such as WhatsApp might want to use the microphone, the photos, the camera, and also the GPS too. Now let's put ourselves in the shoes of the developers. If I wanted to develop an app that uses the camera of a particular device, and I know that multiple hardware manufacturers build different cameras with different specifications, I would be forced to develop individual elements of my software to talk to each different hardware available out there. And this is quite unfeasible and quite hard because the hardware is updating all the time, and the way we should communicate with the camera might be different all the time. Rather, what I want to do is, hey, let me talk to someone who offers me the camera as a service, someone who allows me to access the hardware's API. And all I need to do as a developer of this particular software application is that I need to know how to communicate with the API of a given operating system. In this regard, I need to know how to talk to the camera API of Android or to the camera API of iOS. I don't need to worry about the specifics of the underlying hardware. I only need to talk to the API of the operating system. The operating system in turn is not worrying about how is it that all the other applications that exist out there, the thousands of applications out there, are coded. They only know how to service the camera API for them to use it. So the usage of APIs significantly simplifies the way that multiple heterogeneous applications can use multiple heterogeneous hardware, because we only need to speak the same language of this API that is exposed by the operating system. Another API that you might have used in the past yet not be aware of it is the API of Google Maps. Google Maps is this system of geolocated roads, places, and real-time data that Google offers to different applications such as TripAdvisor. And if you think about it, how is that TripAdvisor has maps of every single city and knows how to give us addresses to different places? This example is TripAdvisor showing us restaurants in Quito in Ecuador. There's no way that developers in TripAdvisor went on to Quito to map every single location in the city. No, what they do is that they access the Google Maps API, which offers them several very useful services. In particular, the Google Maps API tells the developer where each individual place is. Once you know where the place is, Google Maps can tell you what the address is, and it can also even store information about those particular locations. In this regard, TripAdvisor did not program or develop a map. They simply leveraged the map that was already developed by Google, and they communicate with the Google Maps service through the Google Maps APIs. And this is how nowadays applications are built. We don't need to code or develop everything ourselves. We just need to know how to access the services or functionalities offered by others by means of APIs. So far we have developed examples where one application talks to one other application. But application architectures have developed and increased in complexity greatly, and now we have many contexts where many applications talk to many other applications at the same time. And this is the point where the concepts of integration platforms or integration buses come into play. What is an integration bus or integration platform? is a software designed to enable the integration or real-time communication between multiple applications at the same time. And an easy way to tell you about this is to give you an example of how we manage our systems at Inkai Business School. Basically, we have a lot of students that make use of many different softwares, and all the softwares talk to each other. When a student first appears in our business school's radar, chances are that student is going to appear in our Salesforce CRM. We have a lead of someone who might become a student of ours. Now, the moment that this student decides to enroll, several things happen at the same time. On one hand, we must start handling the billing and invoicing of this student. For this, we have Salesforce communicate with our Microsoft Dynamics ERP system. This is where we have a record of a student that exists, and we have all the accounting records for this particular student. Now, we do not only care about the accounting aspects, we also care about the academic aspects. And at Inkai, we use Power Campus, which is a software that enables us to know who is enrolled in what courses, what scores did each student take, and more broadly speaking, manage all the academic part of the student as he passes through our courses and classrooms at Inkai. When Salesforce told Inkai that the student existed, then the student must have been created in Microsoft Dynamics and in Power Campus too. But not only there, at Inkai we also use Google Apps for Education, and we need to create a new email account for this student and give him access to Google Drive, Google Mail, and all the different applications that Google offers us. Once again, once Salesforce told Inkai that this student exists, we need to create the Google account. And the story does not stop there. We have an online learning management system, we use Moodle for this, where we have the courses that were integrated with Power Campus, and the students must have access to this. So now suddenly it's not only about students. Now whenever I create a course in Power Campus, this course must also exist in Moodle, and the users that go into Moodle are the same accounts that come from the Google Apps. And suddenly all the applications must start talking to each other. When the courses end, we need to rate the faculty's performance, and we use a rating system called Blue that interconnects with everything else. So all of these various and heterogeneous systems that do very different things all work together and communicate with each other through this integration platform. Moving more towards our backend, we have a software called LegAdmin, which we use in Central America to manage payroll in our particular context. And you have another software called RecLogic, which we use for our purchasing processes within our institution. These two systems, the LegAdmin that manages payroll and the RecLogic that manages purchases, both interact deeply with the ERP system because that's where we manage all our finance and inventories and materials that we use across the institution. If you think about it, this is a very, very complex ecosystem of multiple applications talking to each other. But in reality, this is actually a very simple ecosystem of applications when compared to large multinational corporations that have hundreds of applications talking to each other. The only way to achieve this is through what we call integration platforms. So far in this video, we have spoken extensively about how different software elements communicate with each other and interact with each other. But we haven't elaborated yet on how is it that these software applications are actually installed, and how is it that we build each of these elements. Now we're going to devote some time to what we call the software stack. The software stack, in layman's terms, is all the software that we need for an application to run. All what we need from the ground up to have an application run. All application must run on hardware. We need processing power, we need places where to store our data, we need hard drives. On top of this hardware, we can install an operating system that enables all the applications to leverage the hardware of the server we're working on. And on this operating system, we might be installing a database engine, an application, and maybe a web server to serve the application. All these three elements communicate with each other and run on top of the operating system. And this is a very broad yet decent representation of a software stack. Let's put some names to these elements, and in particular talk about what we call a LAMP stack. The LAMP stack is perhaps the most popular software stack out there, and its popularity is driven mainly because it's entirely based on open source software. The LAMP stack is a hardware running the Linux operating system, and on this Linux system we have a MySQL database that is running a PHP-based application that is offered through a web server that will quite likely be an Apache web server. So MySQL is an example of a database server. Nowadays, it could also be Maria Database, which is another database engine, which is also open source. The application does not necessarily have to be a PHP app. And I have here WordPress in parentheses because WordPress is one of the most popular PHP applications out there. This application could also be written in Python or Perl. Coincidentally, they all start with a P. And the web server, now we have not only Apache, but also we have Nginx. But overall, this idea that we have a web server, an application server, and a database server, such as in a LAMP stack, has prevailed in many different contexts in IT. What I'm showing you in this diagram is a LAMP stack that is all installed and running within a single hardware. So we could have a single piece of equipment, a single server, or even a laptop, and install all those three elements within this physical hardware. But that must not necessarily be the case. This could also be installed in two different hardwares. And we could have the application and web server on one physical hardware and have the database server run on another physical hardware. Note that the three software elements, the web server, the application server, and the database server, are still communicating with each other, even though physically they're actually installed on independent hardware. Now let's take this a step further. In many organizations, it is too expensive to have individual hardware equipment for each individual server. Rather, what we want to have is a big, large, very capable hardware, and to some extent segment that hardware into smaller units in what we would call virtualization. And the easiest way of conceptualizing virtualization is thinking about having servers within servers. Let me give you an example about this. Let's assume that we're in an organization that has 4 applications. It has an informative web page, it has a manufacturing system, it has a marketing campaign system, and it has a sales and management system. Different applications. Before virtualization, we would have each of these applications run on an independent hardware. Basically, we have 4 independent servers and have each application installed on each individual independent hardware. Now, these applications can be very heterogeneous in nature. The web page, for example, might be running Linux and have MySQL server. It could be running PHP and Apache. This is basically the same LAMP stack I just showed you. But the specialized manufacturing application might not run atop Linux. It actually runs on Windows. So what I have is physical hardware with Windows installed in it. And since we're using Microsoft, chances are we are also using Microsoft SQL Server as our database, and that our application was developed in Microsoft.NET. The marketing campaign software could also be running in Linux and use a slightly different version of MySQL. It could be the same MySQL, I just want it to be different for the purposes of this example. And the application could not be developed in PHP, but it could also be developed in Java, a different programming language. And finally, we had the sales app, which is basically another open source based software, but in this case, the database is Maria Database. The application was developed in Python, and the web server is in Apache again. Now, what we have then, summarizing a bit, is that we have very heterogeneous applications, each running on independent hardware. Now, this is very expensive, and to some extent, it is not flexible enough for firms. What a firm would rather do is, instead of having physical hardware, kind of omit this physical hardware and install these same software stacks within virtual hardware. And where does this virtual hardware come from? It is not vaporware, it does not exist in the middle of nowhere. It is actually part of a larger physical hardware. Think on perhaps a mainframe that has much greater capacity. If each of the other servers was a 2, 4, 8 gig RAM server, this large physical hardware we need now is a server with 64 or 128 gigs of RAM. Very big hardware. On top of that, we're going to be installing an operating system. And on top of this operating system, what we will have is a virtualization engine, or virtualization software, more formally called a hypervisor. And what this software is going to enable us to do is segment or subdivide our physical hardware into virtual hardwares. And this is the software that's going to say, well, to that web page that I had, out of the 128 gigs of RAM that I had on my physical hardware, let me give 16 gigs of RAM to the server running the web page, and let me give 32 gigs of RAM to the manufacturing service. Let me give another 16 and another 16 to the marketing and sales department respectively. What we're doing then is dividing the big chunky physical hardware into virtual segments at a logical level. It's not that we're cutting or rewiring the physical hardware, it's that via software, each individual application, each individual server actually thinks that it is running on its own independent hardware. Now this has one big problem, and you can see that I have multiple instances of Linux running in a kind of redundant fashion within my servers. I have not only a baseline operating system, but I have operating systems again within each individual virtual server. And over the recent years, the industry has moved past virtualization into smaller processing units that we call containers. And what we're trying to do is to load on each container only what is strictly necessary for each individual application to run. How does this work? So once again, we have the physical hardware, and on top of the hardware we have an operating system. But rather than having a virtualization engine, what we have now is a container engine. And by far the most popular container engine out there nowadays is one called Docker. How does this work? Let's look at that web page we had before. Remember that web page was a Linux server that was running MySQL, PHP, and Apache. But what if instead of installing a full-blown Linux and an independent operating system for this web page, what I have is that I allow that this web page application leverages, piggybacks, or reuses some of the core elements of the host operating system, which was also a Linux. If I allow this, then where I'm going to host or contain the web page application, I then no longer need the full-blown Linux operating system. I only need the MySQL database, the PHP engine, and the Apache server to run the application, sharing all the Linux elements that are part of the host system. I can do the same for the marketing application. Even though the marketing application was using a different MySQL version and it was code on Java rather than PHP, it still can leverage the same shared resources from the underlying Linux operating system. And the same happens for the sales application. Note that once again, what I'm not having that I had before is that I no longer have 3 different versions of Linux within each of the 3 virtual servers. I only have the core elements needed, and I'm sharing from the host machine the elements of the Linux operating system needed for the individual applications to run. Now, we did have an issue with the manufacturing application, which did not run on Linux. This application ran on Windows. Well, the way I solve this is that I make my container a little larger such that it can fit a Windows installation, and then my manufacturing container will be slightly larger than the other because it does not only host the Microsoft SQL Server and the application development.net, it also hosts the operating system, in this case Windows. So these are containers, and both in the virtual servers context as in the prior physical hardware context and now in containers, one common denominator across these is that the entire application is running within a software stack. And the entire application might be an e-commerce website, for instance, and the application will handle inventories, it will handle accounts, it will handle invoicing, it will handle all the various elements needed for the entire e-commerce application to run. But what if we could divide this and that we had different applications running each of the individual functions that this broad application must run? This is what we nowadays call microservices. And what we're trying to do is build applications and not divide them by physical hardware requirements or software stack requirements. We'd rather try to subdivide them by functions. And that same e-commerce application I was telling you about, we could divide it between an accounting service, an inventory service, and a shipping service. Each of these services has its own database, and each of these services is accessible to other elements or to core applications by means of APIs. So think of ourselves developing a mobile application that will enable a retailer to sell products online. This application does not have to be a full-blown ERP e-commerce website. However, it must have the mechanisms to interconnect or to access services in loosely coupled and collaborating architectures. So for the application to run, I will need the account service, the inventory service, and the shipping service, but I won't necessarily need them all running at the same time. So I'm thinking in a much more loosely coupled architecture where I only access different parts of the application when I need them. Each service implements a narrowly set of related functions. This has a couple of advantages, which are that each individual service can be developed independently. So I can very dynamically start changing, upgrading, modifying different parts of the service without having to worry about the integration of the application as a whole. However, in the same way as client-server architectures became more complex when we had more moving parts, here we also have quite increased complexity given the different moving parts. But we have several benefits in the sense that now I don't have to develop a full application, I just need to develop services. And these same services that are accessible through a mobile app could also be accessible to a web-based storefront that is accessed through a web server. This is much more dynamic, enables me to access resources of multiple vendors, multiple hardware, multiple technologies. It is much more flexible and much more akin in that regard to the way applications are now being developed, especially with the advent of cloud services and the whole idea behind IT as a service. Everything's now turning into microservices. With this, I reached the end of this video. And I hope that even though all the concepts that we have covered in this video might be novel to you and not entirely clear to you, at least you have a broad understanding of how things are going. The intention of this video is that now you can start asking new and more interesting questions to engineers who are actually the people behind the development of these applications and start understanding what are the business implications of the different design decisions that engineers make when they're designing application architectures. Thank you so much for your attention.